after first criteria of Nyquist first criteria for 0 ISI, let us consider the signaling with controlled ISI, that is partial response signals. The Nyquist criteria pulse results in a bandwidth somewhat larger than theoretical minimum that we have seen. If we wish to reduce the pulse bandwidth further, we must widen the pulse. So widening the pulse may result in interference with the neighboring pulses, right? However, in the binary case, when just two symbols, generally binary situation, we have two symbols, a known amount of ISI may be permissible because there are only a few possible interference pattern. So now consider this pulse, a pulse satisfying this criteria, say NTB equal to 1 for n equal to 0 and 1 and 0 for all other value of n. So consider this type of pulse shape. This is 1, also consider another pulse, similar type of another pulse. So this one is again 1 here and 1 here and 0 here. This is for a particular symbol. Now if you consider a polar symbol, so the pulse will be just in the opposite direction. So instead of +1, it will be say -1. So consider this type of pulse. That means logic 1 is transmitted by PT and logic 0 will be transmitted by say -PT, something like that. The received signal is sampled at t equal to NTB, here, 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 and so on. And the pulse PT has 0 value at all the value of n except n equal to 0 and n equal to say 1. That means for this solid line pulse, it has got a value of 1 at t equal to 0 and t equal to TB. Similarly, this dotted line pulse has a value of 1 at TB and at twice TB, and in all other sampling instants it is 0. Here it is 0. Clearly such a pulse cause 0 ISI with all the pulses except the succeeding pulse, right? Therefore we need to consider the ISI with the succeeding pulses only. So it will interfere, definitely it will interfere, but it will interfere with the previous or next pulse only, because all the other pulses will give the 0 value at that particular instant of time. So consider two such successive pulses located at say 0 and TB. If both pulses were positive, the sample value of the resulting signal at t equal to TB would be 2. For example, this one. Here, if you consider at time TB, we have one value for this solid pulse and one value for this dotted pulse. So total value will be 2. Now if both the pulses were negative, then we should have -1 for solid pulse and -1 for this dotted pulse. So effectively we should get -2. But if we have two opposite polarity pulses successively, then for the first pulse we would have 1, and for the next pulse we should have -1, resulting in 0. So if we consider this trend, we can design a decision rule for which, say, previous pulse, current pulse, and the interference value, voltage. So if we are now going to, we should write it in this way: received voltage previous pulse, current pulse. This should be the proper way of representation in at the receiver. So the received pulse is now sampled. So sampled value is, say, positive value, say +2. So our decision will be previous bit was 1, current bit is also 1. Now if we have received voltage negative, that means previous pulse was 0, or previous bit rather, bit value. So previous bit was 0 and current bit is also 0. Now if the sample value is 0, then we have two different conditions. Condition is, if previous value was 0, then the current bit will be 1, just reverse. Similarly, if previous bit was 1, then the current bit will be 0. So this will be our logic for the at the receiver. For example, just take an example, nothing else. Say we have to transmit these bits. We are taking a small bit, we can extend this idea for a larger bit also. So what happens, if this was the transmitted sequence, then the samples of this sequence would be like this: 1, 2, 0, 0, 2, 0, and so on. Because previous bit was 1, current bit is 1, so 1 plus 1 is 2. So in this way we have transmitted the signal. The samples values are like this. Forget about the first one. So detected signal, or detected bits rather, how we can decide the previous bit. This is not the known previous bit actually. This one is known previous bit. We have to know the previous bit. So we have a positive value. So previous bit was 1. So the current bit will be 1. Now we have the 0 value. That means this is the condition, 0. And the previous bit was 1. So current bit will be 0. Again we have 0. But the previous bit was 0. The current bit will be 1. Here we have 2 positive value. So previous bit was 1. Current bit is also 1. Here we have 0 with the previous bit of 1. So previous bit of was 1, so current bit would be 0. So in this way we can determine the detected bits, and as you can see that transmitted sequence and the detected sequence are the same. So this is how we can implement, though ISI is there, but in presence of ISI we can still able to detect the signal. Now this pulse goes to 0 at t equal to minus TB and TB and 2 TB, resulting in a pulse width of 50% higher. Sorry, the pulse goes to 0 at minus TB and plus 2 TB. So its pulse width is 50% higher than that of the Nyquist criteria pulse. This results in a reduction of its bandwidth. So this is the second method proposed by Nyquist. The scheme is the controlled ISI, or also called the correlative or partial response scheme. A pulse satisfying the criteria, this criteria of controlled ISI is the duo binary pulse. So if we restrict the pulse bandwidth to RB by 2, we can show that only this pulse PT meets the requirement of the Nyquist second criteria for the duo binary pulse, PT equal to sine pi RB t divided by pi RB t 1 minus RB t, and its Fourier transform will give us the p omega 2 by RB cos omega by twice RB rectangular function omega by 2 pi RB exponential minus j omega by twice RB. So this pulse transmit binary data at a rate of RB bits per second and has a theoretical minimum bandwidth of RB by 2 Hz. So this equation is showing that this pulse decays rapidly as a decays at a rate of say 1 by t square. This pulse is not negligible. This is actual pulse is difficult to achieve because it is non-causal in nature and it has an infinite duration, but we can have some close approximation of this pulse. Now raised cosine pulse satisfies the criteria for the partial response. So thus the data transmitted by the raised cosine pulse can be detected using Nyquist criteria for 0 ISI or using the controlled ISI method. Problem is that it requires the twice bandwidth as that of this pulse. So this is what we have to say about this intersymbol interference.